So this is the final lecture that I will be having on chapter 3, and we will be speaking about electrostatic approximation and a little bit about the potentials, so that in case you ever need to encounter a so-called potential formulation of electrodynamics, at least you roughly know what we're speaking about. So I will be going through the main things regarding the electrostatic approximation. Physically, this situation corresponds to the cases that the electrons do not move, so electric charges that give rise to the electromagnetic radiation and fields, the source terms do not move, so no J here. And then I will be speaking about the application of Gauss' law and how we can derive a Poisson equation, and then how, for example, does the Maxwell and Faraday law look under the electrostatic approximation. And then I will be speaking a little bit about the properties of the electrostatic field. So mainly that it's irrotational, so that it's curl-free. And then I will be speaking about the Helmholtz decomposition. And this, of course, gives a little bit more flavor on the structure of the electrostatic field. And then I will be showing you the Poisson equation and formulate the Gauss' law in a potential form. And then I will be saying a little bit about the kind of how do we generalize from here. So I will be showing the way to define the scalar potential phi and the vector potential A. And then that gives me the basis that how we could go beyond into the potential formulation of electrodynamics. But like I've said already many times, this is a topic that goes beyond our scope on this course. So we do not speak more of the potential formulation. So the wave equations that we form and use, we write them and we use them for the E fields and B fields and not for the potentials. But in some cases, the potential formulation will be more beneficial to use. So please be warned that there are instances that it would be better to resort using that one. So what we will be starting with is that I will just start by going through the basics, and this helps us also to kind of get a better grasp of the vector calculus operators that we just introduced in the previous lecture. And of course, we can look into the fundamentals of electrostatics at the same time. And please note that in electrostatics, we do not really have propagating electromagnetic fields, so no light is propagating inside our system, but rather electrostatic approximation holds. So we have static fields. So we have a static electric field, and we may have a static magnetic field in the case of a magnetostatic approximation holds. And here, to get started, we assume that electrostatic approximation applies. And what this means physically is that the electric field that we may look into, so that we may have an electric field, but the field is caused basically by stationary charges. So stationary means that the charges do not move. And in practice, in electrodynamics, most of the time we only need to worry about the electrons and how they are moving around. So here, under electrostatic approximation, that just means that our electric charges do not move. And of course, they give rise to electromagnetic fields, and they do act as the sources, but they do not give rise to radiation. So they give rise to fields, but no radiation. And in this case, when we take and look into the Gauss' law, which combines the electric charge density ρ with the electric field, and here particularly we use the integral notation, we may write the Gauss' law that we integrate the electric field over a closed surface. That's what the definition here means, or the notation here means. So we are calculating a surface integral over a surface S. And since we have this circle encirculating the integral nodes here, this surface is actually enclosed. It's a closed surface. And then we are looking at how the field forms, or like how the field looks like at the surface element, differential surface element dA on the surface. So it's a 2D integral, surface integral, and this is equal to the case that we would calculate the volume integral. So this volume now is the volume that is enclosed by this closed surface of S, and here we have the rho divided by epsilon naught inside as an integrand, and then we have the volume element as our differential element. So dA and A here is the vector. That's a shorthand notation of a meaning that we would take the surface normal, unit surface normal, and the differential volume element, differential area element. So this is what this means here. So this in fact is a vector quantity. So would be the same thing as saying that they will take the dot product of the E with the unit vector n pointing perpendicular to the enclosed surface. And in here, this is the volume element. And in many times, we can be doing integrals in the x, y, z basis. So that can be just described that that's the dx, dy, and dz. And this is the volume element of our integral. So the left-hand side of the integral is, as mentioned, over a closed surface S. And another way of saying that this is then enclosing also the volume V. We could just write that this closed surface S equals to dou V. And this notation emphasizes the point that we are enclosing a volume of V. And on the right-hand side, we have the volume integral, and this is over the volume V. So dou V is the V's surface. And this, as I said already, this is known as the integral form of the Gauss's law. I think we have encountered this already before in our kind of like a basics physics course, engineering physics, in the first years in the university. And in the context of our course, the thing here is that we want to transform this integral equation into a differential form, because when we are operating on these entities with the differential form, or using differential form, it's way easier than describe things using wave equations and differential equations. So instead of using the integral form, and of course these are entirely equivalent, so it doesn't really change the physics. You can calculate things either way, but we are interested in formulating a wave equation, and subsequently we want to transform these integral forms into a differential forms. And how do we do that? Is that we take use of the divergence theorem. And the divergence theorem basically says that this guy here, we are having a surface integral over a closed surface of this guy over the surface normal unit vector. This equals of calculating into the divergence of the E. And then we are performing a volume integral over the volume that we are enclosing. And then we end up with a situation that we have two identical volume integrals on both sides. And here we have the divergence of the E. And then we have here the volume integrand as rho per E. And since this must be fulfilled, this equality for all volumes V that we can imagine, we can get rid of the volume integrals and we can instead look what are the integrals. So all kinds of volumes, this equality must hold, and this means that we can in fact get rid of the integration at all. We could just imagine that we just enclose, we make the volume of integration smaller and smaller and smaller, and then in each of those points, the equality between the integrands must be applied, must apply. And then subsequently we get with this differential form for the equation. So because in all points the equality must hold for the integrals, and we can arbitrarily choose what kind of volumes we are integrating over, the integrands must in fact also be equal. And this gives me the fact that the divergence of the E field must be equal to the rho per epsilon naught, so the electric charge density divided by the vacuum permittivity. So both ways of formulating Gauss's law, of course, mathematically they are entirely equivalent, but as I already said, we focus on the differential forms or differential formulation, not to confuse with the differential forms that are mathematically on their own kinds of entities. We can more easily form wave equations. And wave equations, basically, they're always given in a differential form. So that's the kind of reasoning we have on this course. Let's now progress forward. So we have now formed the Gauss's law and how it looks like under the electrostatic approximation. And it looks exactly like it does also in the general case. But now let's look how does the Maxwell Faraday law look when we are having the electrostatic approximation. And now we have stationary charges, and this means that we don't have moving electrons. And this means that we don't have electric current density J here. So that J is identically 0, because J, of course, we can define that that's the electric charge density rho times the velocity distribution of the electrons. And since we don't have moving electrons, we always have J equals 0 in here, because the charges are not moving. They are stationary. That's the main principle under the electrostatic approximation. And what this means is that we do not have any time-dependent magnetic fields, because the source term giving rise to time-dependent B fields J is equally 0. And now we can look how does the Maxwell Faraday's law look like. And the Maxwell Faraday's law is giving that it's the curl of the E field, and this is equal to the minus time derivative of the B field. And we know that the right-hand side must be equal to 0 vector. We see that this actually restricts the type of the E field. So that the E field, we know that it can be non-zero, we can have an electrostatic field, but whenever we calculate the curl of this electrostatic electric field, we know that we get a 0 out. And this means that the electrostatic electric field is irrotational, so curl-free. Or if it would be working more in the context of hydrodynamics, this mathematics would be said that my E distribution here is laminar, my vector field. This is the more conventional notation one says when we are looking at hydrodynamics, how liquids are flowing around. And if you would be looking differential equations to understand how liquids move. So this is quite nice already. By just looking at the Maxwell's equations and applying them to our situation, we already have learned a great deal. So this is actually quite a bit of information to know that the E field is irrotational, so that this applies. And this is now a kind of good thing to remember. This is also known as the fundamental theorem of vector calculus, and it sounds very important, and this is in fact what it is. And what this statement says, the fundamental theorem of vector calculus, is that this says that when we have an electric field, and if it's twice differentiable, of course, like in our case, we want the electric field to be twice differentiable, the E field can always be decomposed into two different contributions. So we can always write any E field in this kind of form, where the first term is minus gradient of phi, and this phi really indeed, in the case of electrodynamics, would be our scalar potential. And then this is an irrotational term, so that if I would calculate the curl, this would be basically all that would be left. And then I have my other term, and this would be of calculating the curl of a so-called A term, which is known as the vector potential. And this term is entirely solenoidal in terms of vector field properties, so that if I would take a curl of the E, this guy will be basically, if I would be taking the curl of E, this term is everything that will be left, this guy here. But if I calculate the curl of this, I know from the previous identity that if I calculate the gradient of something and then I calculate the curl, I get a 0 out. So that this term, if I would calculate curl, would give me always a 0 here. This decomposition is also known as the Helmholtz decomposition, and it's extremely useful at times. So please at least acknowledge the fact that there are these kind of ways that we can describe vector fields, that they do have different kind of structure, a specific type of structure and specific properties. So this is somewhat similar, of course, a lot more abstract and more general, but when we would be looking, for example, numbers, like integer numbers, and we could say that these numbers, we can classify them either as being odd or even valued. So in somehow similar, we could say that when we have this kind of electric field, that there are these different contributions that they depending on how the field actually looks like. And this is at least I think very interesting to see that the physics that we are dealing with in our universe, it seems to be having this kind of specific structure, and subsequently the math has a given kind of structure. Now let's look more into the Gauss's law and how we could transform this into the potential formulation, because I want to show you here that there is also a different way of describing electrodynamics that is not based on the E field and B field, but rather on the potentials, on the scalar potential and on the vector potential. And how do we do this? Is that we transform the Gauss's law into the potential form. So the Gauss's law, we calculate the divergence of the E field, and this of course was equal to the rho divided by epsilon naught, the vacuum permittivity. And in here we just transform this divergence of the E into a description using the scalar potential. So basically, we can place in instead of the E field and calculating the divergence, we can use the definition of the E field here, that we can calculate the gradient of the scalar function and then calculate the divergence minus E. And please note, this is exactly, maybe I should go back. So basically what we are using here is that we are taking use of the Helmholtz decomposition. So we are writing E using these two terms, and what's left is that the second term vanishes. We do not need to worry about that. And then what's left is that we only have the gradient of the scalar potential with calculating the divergence of that minus. And now we know that this can be also written, it's a Laplace equation, so we can also just write that using this upward triangle to the power of 2. And then, since this is the Gauss's law, this must be equal to the rho divided by the epsilon naught. So these are just the notational things that the Laplace operator, we can either write it using the triangle pointing downwards, squared, or the triangle upwards, but this is just the Laplace operator. And now we have the Gauss's law using either the E field, and we calculate the divergence, and here we can calculate the Laplace of the scalar function. And this is different way of doing things. So this Laplace of a scalar function, which is equal to minus rho per epsilon naught, this is known as the Poisson equation. And if you want to solve electrostatic fields, this is often way easier differential equation to solve than the original divergence equation that we just started with. You might be wondering how this is the case, and a kind of simple thing that maybe hopefully explains to you quite well already. This is a vector field. So dealing with vector fields, it's a lot more complicated than dealing with a scalar function. So phi is a scalar function, and this is a vector valued function. So when we describe Gauss's law as a Poisson equation, we do not need to deal with vector fields at all or vector valued functions, but we can just calculate the Laplace. And this is subsequently a lot more easier than to calculate divergences of vector fields. So this is the kind of motivation why one would want to go into the potential formulation, because things are a lot more easier in that way of describing things. So this can be looked either way. Either we can think that we have the E field, we have the electrostatic field, and we want to solve that. So we can either do that by solving phi and then calculating the gradient of the scalar potential. So essentially we take use of this equality, and this is one way of doing it. And then we are left out of the information. We have solved the Gauss's law. So we can either start with the phi and we solve the Poisson equation, and then when we have done that, then we can know what is the phi, what is the scalar function, and if we want to know the E field, then we can simply calculate the gradient, and then we get the E field. So this is one way of doing solution, like solving these kind of differential equations. and this has been highlighted into the figures. So there are different cases where we can see how the electric fields are, and we could be, for example, looking at a charge, just an electron here in a homogeneous space, and what kind of electrostatic field it causes. So it causes this kind of like a curl-free field, irrotational field, And basically the irrotational field means here that I'm drawing a circle, a sphere around my source, my electron, and then I'm drawing lines, and these lines correspond to my E field. And in all locations, in all of the spheres I can imagine, the E field is always propagating through the sphere at normal incidence, perpendicular to the surface. And this is what physically it means that I have a curl-free field, irrotational field. And here I have a case, another scenario that this kind of potentials and fields I could solve under the electrostatic approximation. I have an electron, negatively charged particle here, and I have positively charged particles here, and then I can solve what kind of electrostatic fields I have. And still, under electrostatic approximation, when I'm drawing a curve like this, the fields go seem to be going perpendicularly to this surface, so that the field has a given kind of structure, although it looks quite a little bit more complicated than in the case of just a single charge in a homogeneous space. But these kind of problems can be solved when we are dealing with the electrostatic approximation, so that the charges do not move. And then we're left to essentially solve Poisson equations, and that's it. Nothing more complicated. But in the framework of this course, we should remember that the solutions of the Poisson equation, so that the scalar potential we get out and the subsequently calculated electric field, that does not fulfill the wave equation. And what that means physically is that the electrostatic E field does not propagate. It is a static electric field. And what it means is that it doesn't correspond to light. It's not propagating electromagnetic radiation. It is a field, but it's not a field that is transferring energy from point A to point B. So that it is rather just a static field. It can change, it can accelerate charges. No doubt about that. Recall the Lorentz law, Lorentz force, but it doesn't manifest itself as a dynamic radiation. It's not propagating light. And finally, I just mentioned that there's also another regime, so-called magnetostatic approximation. And in this case, we can use that to understand and describe some of the electromagnetic phenomena where the magnetic field is not time dependent. So we have a static magnetic field. And when we are dealing with this approximation, it's very smart to define a vector valued potential A and then use that. And this is also known as the vector potential. And in this case, we would be having the E field and the B field, the magnetic field, described using these two potential functions. So we have the phi, the scalar potential, and we have the A, the vector potential. And then the B field would be defined using them simply that it would be the curl of the vector potential. And then the E field will be the minus gradient of the scalar function. And now we have the addition arising from the vector potential minus the time derivative of the vector potential. And then under the electrostatic approximation, we do not have moving currents. So this term vanishes. We do not have time-dependent magnetic fields. And then we also have this equality between the E field and the scalar potential. And of course, the B field will be untouched in this case. And this, of course, this formulation, we can now relate the E field and the B field with the scalar and vector potential. This would, of course, allow us to describe electrodynamic processes, everything we can imagine, using these potentials. So essentially, we would describe electrodynamics in a so-called potential form. And in some cases, this is highly useful, but in our course, we do not really deal with this. And finally, I would like to point out that when we are dealing with currents, there's a kind of nice equivalence in the description. So if you have a current making a loop, it gives rise to a magnetic field, and it looks exactly the kind of magnetic field that we would see when we have a static magnet in the location of the current. And looking the other way around is that if I would want to realize a magnet, and for example, I would want to realize a very strong magnet that I could lift, for example, cars with that kind of strong magnets, I could imagine that I would have a very strong current, powerful current forming a loop, and that way I would be able to give rise to a strong magnetic fields. So I could form an electromagnet. So these are the kind of considerations and physics we can now see by looking at the math we have just introduced. So I thank you here. I hope this was a useful lecture to you, and I think it's a nice interlude for the next chapter, where we will be going really to introducing the Maxwell's equations to you, forming a wave equations based on them, and then looking all the properties that arises because of the math we're dealing with. So I thank you. I hope you enjoyed the ride and have a good rest of the week. Thanks and bye-bye.